This is a chart mapping global seaborne crude oil trade from 1970 to today. Over the last 50 years, the volume of oil moving across the ocean has undergone a steady and massive expansion. But if we overlay the data for large tanker spills, those over 7 tons, we see a steep 90% decline during that exact same period. As oil in transit reached record highs, the frequency of transit-related spills approached zero. This sharp drop reflects the efficacy of international regulatory frameworks and the universal adoption of double-hulled vessels within the shipping industry. The era of the routine maritime tanker disaster has largely subsided. Identifying modern ecological threats now requires looking beyond standard shipping lanes. Today, major oil pollution events rarely originate from standard vessels in transit. They occur during complex, anomalous blowouts during industrial offshore extraction. The Deepwater Horizon event serves as the primary case study for this modern anomaly. Over an 87-day period, the ruptured well released exactly 134 million gallons of crude oil into the Gulf of Mexico. While the blowout originated at a single point on the ocean floor, the resulting oil slick spread to foul 1,300 miles of shoreline across 5 states. To measure the true impact of modern marine oil pollution, we must separate the global statistical decline in tanker accidents from the specific micro-ecological damage mechanisms that occur during these high-volume anomalies. When oil enters a marine environment, it does not cause a uniform type of damage. Environmental injury is dictated by a specific physical-chemical spectrum. This graphic maps 2 opposing poles of damage. On the left, light oils have high biological availability, entering the food chain to cause systemic failures. Conversely, heavy oils on the right have low biological availability, but persist in the environment, causing physical smothering and asphyxiation. An oil spill's lethality profile isn't determined strictly by volume, but by where its chemical composition lands on this toxicity to smothering spectrum. How a local habitat reacts to that spectrum depends on 2 ecological metrics: vulnerability and sensitivity. Vulnerability is a spatial metric. It measures the physical likelihood of an organism coming into direct contact with surface oil based on its habitat zone. Seabirds exemplify high vulnerability. Species rafting in flocks on the open water place themselves directly in the path of floating oil. Sensitivity is a physiological metric. It measures the acute biological reaction of an organism or habitat once contact has been made. Mangrove forests are highly sensitive. Relying on specialized breathing routes to draw oxygen, the tree suffers rapid asphyxiation when those pores are coated in oil. The most severe ecological impacts concentrate where these 2 metrics meet, when highly vulnerable populations also possess highly sensitive physiological traits. We can see the light oil toxicity model play out directly by looking at the estuarine habitat of Barataria Bay following the Deepwater Horizon spill. The local bottlenose dolphin population served as the primary subject for tracking the toxicity mechanism. The specific chemical compounds of the spilled oil permeated the water column and local prey. This created high biological availability for the dolphins. This chart displays the result. Over the years following the spill, the Barataria Bay dolphin population suffered a 50% decline. This drop was rarely driven by immediate acute death. Instead, the toxic exposure caused long-term systemic organ damage and widespread reproductive failure. Light oil toxicity acts as a delayed-action population killer. It erases the next generation of a species rather than immediately killing the current one. Operating simultaneously during that exact same Deepwater Horizon event was the heavy oil smothering mechanism. The juvenile Kemp's Ridley sea turtle exemplifies physical miring. Here, thick, heavy oil completely coats the shell and limbs of the animal. Heavy surface oil infiltrated the open ocean sargassum habitats, transforming what is normally a floating refuge for young turtles into a physical trap. Once mired in the oil, the turtles suffered decreased mobility. This led to rapid exhaustion, dehydration, overheating, and a complete inability to evade predators. Up to 20% of all oceanic juvenile Kemp's Ridley turtles present during the spill perished directly from this physical exposure. Unlike the dolphin's delayed population decline from systemic toxicity, the turtles' smothering deaths were physical, immediate, and acute. A single megaspill triggers multiple, distinct mechanisms of population destruction simultaneously across different species. Based on these mechanisms of damage, what is the actual mathematical timeline for an ecosystem to repair itself? This Gantt chart plots natural recovery windows across marine habitats. Plankton rebound in weeks through massive overproduction. High-energy rocky shores take 1 to 5 years as wave action aids cleaning. However, sensitive mangrove forests require a decade or more to return to normal functioning. The broad concept of ecosystem recovery is a mathematical average. While the macrosystem often rebounds quickly, specific sensitive micropopulations face multi-decade generational gaps. These specific biological recovery timelines bring us back to the macro statistics we examined at the start. This plot reflects 50 years of success in evolving maritime safety standards. Large tanker spills have been reduced to a statistical minimum. Environmental policy must now focus on the specific sites of anomalous megaspills rather than traditional shipping routes. Protection now requires pre-funding precise, multi-decade restoration plans, specifically targeting high-sensitivity, slow-reproducing habitats that lack natural resilience. Modern environmental protection involves managing the complex chemistry of industrial extraction and targeting the specific vulnerabilities of the surrounding ecosystems.